Hello, everyone. Thank you for watching this video. In this video, we will look at some of the strange but interesting aspects of quantum mechanics, namely superposition and entanglement. We will do this by using IBM's real quantum computer. Yes, a quantum computer is already in existence. Sorry. If you have watched my previous video called Transmol Introduction, the link is down below in the description. I hope you might have learned a little bit about the basic building blocks of quantum computer called Transmol. I think I focused a lot on the physics of Transmol, and in the end, I didn't even have time to talk about the quantum computer itself. So in this video, I hope to remedy that. Like I said, a real quantum computer is already in existence. It is built by IBM, and we can all register for an account here for free. And we can start playing with it. As you can see here, I have built myself some quantum circuit that I hope can do addition for me, but by the look of it, it doesn't look quite right. It's a mess. So let's start with something simpler. So let me share my screen. Okay, as you can see, I'm on IBM quantum computer page, and it's a clean slate. And we see on the right-hand side, lines called Q0, Q1, and Q2. Okay, so these are our qubits. They can be either 0 or 1, or a superposition of 0 and 1. Currently, the qubits are all in well-defined state. For instance, all the qubits here start in state 0. Let's put this meter-looking unit, this, down here. And we can see that it measures the state the qubit is in. And the qubit is 100% in the 0 state. There's no other possible value. So this is a well-defined state. Now let's delete this measurement and put down this hard mode gate, H gate, in short, beside our qubit. Okay, what this gate does is it scrambles our qubit. Now it is neither 0 or 1. It is a superposition of both, as you can see down below. Here, it can be either 0 or 1. Let's measure it. So we put down the measurement unit. Okay. It returns one of the possible values, but this is actually just a simulation. This is not a real measurement. This is a simulation of the ideal case. To do the measurement, we have to send it to the quantum computer. So in fact, here we have already completed our quantum circuit. Yay! It's very simple. And let's send it to a real quantum computer. Here, I'm doing this at night right now, so hopefully there won't be any queues. Well, the queue is not very long. This one wouldn't work. It only works for 1 qubit. Okay, they will take some time. But this is usually what happens. You have to wait a little bit for your job to be processed. So just click here. And you can see our job is being processed. Luckily, I have done this already. So let's jump to the result straight away. So let's go back to the slides. So what the result tells us is that there's roughly a 50-50% chance of finding the qubit in 0 or 1. That's what the Hadamard gate or H gate does for us. But it's not perfectly 50%, as you can see. Why? Because a quantum computer system is totally random. You can't expect it to give you 1 0, 1 0 alternatingly, amounting to a perfect 50% for both outcomes. Most likely, it will be a totally random series of outcomes, 1 1 0 0, 1 0 1, etc. And that you might think this is bad, but it can have a surprising usage in cryptology. That is the art of sending secret messages. In cryptology, one needs to generate a random key to lock and unlock a secret message. The problem is, random number generators are in fact based on mathematical algorithms, so they are not truly random. There are patterns, and hackers can find out the pattern with their computers and thus unlock the messages not meant for them. Not with this quantum computer. Now we can repeatedly just measure the outcome of this simple circuit that we have here and get a set of truly random numbers. That is why you hear a lot about using quantum computer in cryptology. Its randomness is its advantage. Okay, now let's go back to our IBM quantum computer. I wanted to say composer, but somehow I mixed it with quantum computer. So this composer basically allows us to build a quantum computer. It sounds confusingly similar to computer. We have seen what a single qubit can do, but obviously the quantum computer can have many qubits in it, not just one. So we can, if we can somehow make them interact with each other, yes, actually we can. We can use these quantum logic gates here. I don't know many of them, but this one I know. This is called the C0 gate. Let's put it on. Before that, let's delete this measurement. Okay, so we put down our C0 gate here, connecting Q0 and Q1. Q1 is in a well-defined state of 0, but Q2 is still in a superposition state because of this H gate, the Hadamard gate. Okay, what does this C0 gate do? If Q0 is in 0 state, it does not affect Q1. But if Q0 is in state 1, then whatever the state Q1 is in, it will be flipped. So for instance, if Q0 is in state 1 and Q1 is in state 0, as we know, it's in a well-defined state, after passing through the C0 gate, Q1 will end up in state 1. So if we measure both qubits, you can calculate it for yourself. The only two possible outcomes are Q0 and Q1 both in state 0, or Q0 and Q1 both in state 1. There's no other combinations such as Q0 in state 1, Q1 in state 0, etc. And we see this in the graph down below here. This is the simulation, as I said before. This is not the measurement result. It's an ideal case. So clearly, state 1, 1 and state 0, 0 are the only two possible outcomes, and they are equally likely. We can, of course, do a measurement on them on the real quantum computer and see what we get. We put down our measurements to complete the circuit, and then we have to again, send it to a quantum computer. And as you can see, even my previous job hasn't been done yet. Luckily, I have done this measurement already. Just a few months ago, when I started using this IBM quantum computer, I don't think there are this many people using it, but I guess it's a good thing. Many people want to try something new these days. So let's look at the result, which I have done earlier. We see that indeed 1, 1 and 0, 0 are the two most likely states. 0, 0 and 1, 1. They are not perfectly 50% because of quantum randomness, as we have discussed, but slightly troubling is that we also see there are probabilities for other states to exist. For example, 0, 1 and 1, 0 here. These are due to environmental noise. The two qubits are also interacting with the environment, which can also alter their states. The probability is small in this case to end up in 0, 1 or 1, 0 states. So the IBM quantum computer is very well built. We call these two qubits entangled because their states are not independent of each other. In this case, the two qubits are always in the same state. If one of them is in state 1, then the other must be 2 in state 1, and vice versa. Now consider this thought experiment. Let's say instead of having two qubits entangled, let's have two particles entangled. And after that, they go their separate ways, but still they are entangled. So if we measure one of them to be in a certain state, the other particle must be in that same state too. It's hard to imagine qubits moving apart since they are parts of the same quantum computer. So anyway, in this thought experiment, suppose they move really far apart and we measure them at the same time. Maybe one of the particles is still on Earth, we can measure it, and maybe an alien collaborator is measuring it on a far, far away planet. If we measure the particle to be 0 state on Earth, then the alien scientists will simultaneously also measure 0 state. Okay, so these two smiley faces are our two particles. And if we measure the particle to be in state 1, the alien scientist will also simultaneously measure it to be in state 1. There's no other way. The two particles must always be in the same state. So even if they are far apart, if one of them is found to be in one state, then the other immediately switches to that state as well. So how do they know what is happening to the other particle? Most importantly, how could they know instantaneously what is happening to their other part? This is called the EPR paradox. Einstein, Podolsky, and Rosen are three scientists, physicists who came up with this thought experiment. Surprisingly, people can prove experimentally that this is indeed the case. The influence of quantum mechanics can travel instantaneously across the universe. So does this mean we can transfer information at a speed faster than the speed of light with our quantum computer? Yes, coming back to our quantum computer. Unfortunately, no. But this strange behavior definitely had people thinking. And there are attempts to make use of this strange behavior in information transfer, such as super dense coding, where one qubit can transfer the information of 2 binary bits. But this is another rabbit hole, and we are way over time. We probably have to do it in another talk. So in summary, quantum mechanics and quantum computer offers a whole new world for us to explore. Let's not be afraid. And here, I might add personally, I do hope that this faster than the speed of light action can lead to faster than the speed of light travel. That is my wild dream. Thank you.